stiff that spring or object is as far as moving. So if you have a very high K, that's very difficult to stretch or compress. And if you have a very low K, like maybe on a slinky, it's very easy to move it around. Now, X is special. And I have it in red here because X, when we're talking about kinematics in physics, is just your position. When we're talking about Hooke's law, however, X has a very specific definition, and it's the displacement from equilibrium. It's not from any other point, but from the equilibrium position. And the negative sign is reinforcing that the spring or whatever is trying to pull back or push back to the equilibrium position. I wouldn't be so worried about the fact that it's considered negative, because on your equation sheet for AP, this equation looks like this, where we're going to take the absolute value of the displacement and the absolute value of the force. So you're really using Hooke's law to find the magnitude of the force. And then you can determine whether you want to call that positive direction or negative direction based on a free body diagram. Okay. So if we're talking about vertical or horizontal springs, vertical or horizontal, typically we ignore friction, and what we look at are called ideal springs. These are springs that have no internal friction, and they can be both stretched and compressed. So the amount of elastic energy that's on our formula sheet can be calculated using 1/2 kx squared, where K is once again the spring constant. This is the exact same spring constant that we had in Hooke's law. X is the displacement from equilibrium, which is the exact same definition that we had in Hooke's law. And we can take a look at the period of this oscillator using another formula that is on your equation sheet. So if you're looking on your AP equation sheet, and please make sure that you have, the AP exam should never be the first time that you look at that equation sheet. You should know where everything is, what is included, what's not included. So all of this is towards the bottom under the list of all the variables. So if you're having one of those days and you forget that M is referring to mass or X is referring to position, all of those variables are defined for you. And then underneath that, we've got some energy and periodic motion equations. So this is the period for a spring, specifically a spring. And we're going to have 2 pi over the square root of the mass applied to it and the K value. So again, it's the same K that we're talking about right here. So what's happening in these next couple of illustrations? If we assume that an object is sitting on a frictionless table, it's pretty awesome that physicists can come up with that. So we have a frictionless table, and we're going to start with this on a spring, pulling it away from equilibrium. The spring is then trying to pull it back to equilibrium. So now we're at equilibrium. And it goes past that. So now the spring is trying to push it to the right against what it was doing before. And this is how we get that oscillation back and forth. At equilibrium, this is where our velocity is going to be at maximum. Now we're not worried about the direction so much, so we'll just look at the speed, hence the absolute value here. So that's where we're going fastest, because all of our energy at that point is in kinetic energy. The spring potential energy here is going to be 0 if the displacement from equilibrium is 0. At the end points where it turns around, so that would be position 1 or position 3, that's where the speed is going to be 0, so slowest, because it turns around. And all of your energy at those points is now in spring potential form. And that's our maximum displacement, either at an amplitude of, say, positive A and an amplitude here of negative A. So as it goes back and forth, this really does show conservation of energy over and over again, where we go from spring potential to kinetic to spring potential to kinetic, back and forth. And then I found a little animation that does exactly that. So here you can see with Hooke's law, the force is always in the opposite direction from the displacement. And as we move farther and farther away from the equilibrium position, we need more and more force. So that fits right here. And you can also kind of see where it goes fastest and then slow, faster, slows down, and repeats. So this is known as harmonic motion. We can also graph this as something that looks kind of like a sine function. So if I pull that spring way out to the right at, say, amplitude A, that spring is going to pull back towards the equilibrium position, move past that to a new amplitude, which pushes it back towards the center, hit the equilibrium position. It continues to move on back to its original, and it's going to oscillate back and forth. And along this horizontal axis, we can look at how much time all of that takes. So if we start at 0 time, at about a quarter of the period, we're back at the equilibrium position, and then a quarter more, we've swung as far to the other side as we're going to, and a quarter more, we're back at equilibrium, and then a quarter more, one full period, we end up back where we started. So we could find the time for the period, if this was marked in seconds, by looking at any point along this sine wave that is repeated. Doesn't have to be from the beginning to, say, this section right here, where it's marked as number 5. We could look at where it goes through the origin, through the equilibrium position, moving from, say, right to left. This is moving left to right, so that's not the same. But here it is, moving through equilibrium from right to left again. So that would be one period as well. Any 2 points that are exactly repeated. Now we also end up seeing harmonic motion in uniform circular motion. So things are moving in a circle at a constant speed. When you are moving in a circle, even if the speed is constant, the direction is changing, so there is acceleration that takes place. And with circular motion, hopefully you remember that the acceleration points in a particular direction. It's known as centripetal acceleration, which literally, we break down the meaning of this word. Is center pointing. Okay, so centripetal acceleration, it is pointing to the center of the path. So you can think of that C for a circle. You can think of that C for center. You can think of that C as centripetal. It all really means the same thing. And that is also on your equation sheet. The velocity, however, is always perpendicular to acceleration. The velocity itself is tangential to the circle path. So if this is our circular path, the velocity is tangent to the curve at whatever point, whereas the acceleration points to the center. And those are always going to be at a 90-degree angle to each other. All right, so let's talk about vertical springs a little bit. Let's say I have a spring that's hanging like this with a mass on it, and I'm going to let it bounce up and down. I can graph the displacement, the acceleration, the velocity from point A to B to C to B to A, and let it repeat. So if we have, say, a steel ball or something like that hanging on a spring, equilibrium we'll call point B. And then I'm going to pull it down to C and let it go, and it's going to bounce up to A and come back. So I can look at its displacement following this sine-like curve. Shift it over a little bit, but that's fine. And I can look at the velocity. I'm going to skip acceleration for just a minute. So looking at the velocity, it moves fastest when it goes through equilibrium and slowest at points A and C where it turns around. And we can see that the velocity is maximum at the equilibrium position, and it is 0 at A and C where it turns around. And then acceleration ends up being the opposite of displacement. And then again, I found another animation for you. So this is what we're talking about. We can look at how the amplitude changes, our maximum displacement, and where it's fastest and slowest. Now, looking a little bit more closely at vertical springs and their energy. So we're going to look at 6 different positions along the path. If this is at equilibrium, we'll start off, it's just hanging there. Then it's not moving yet. There's no force acting on it. It's just sitting there. If I then pull it down a little bit, the spring is trying to pull back up. It's moved some displacement. At the maximum displacement, our velocity is going to be 0, but our force pulling back is also at a maximum. There's no kinetic energy there because velocity is 0, but our potential energy is maximized there because of 1/2 kx squared. X is this d value. Then it comes back to equilibrium. If I let go of it, the spring is going to pull it back at the equilibrium position. That's where our maximum velocity is going to take place. There's no more spring force acting on it, but it does have a maximum kinetic energy and no spring potential energy there. It continues to go past equilibrium and turns around. Now the spring is pushing back down. So at the turning point, velocity 0. The net force is pushing back down. It's at its maximum value. The maximum potential energy, and 0 velocity means 0 kinetic energy. We get back to equilibrium and it repeats. It's just going in the opposite direction. And then it's going to swing back up. If you see something with pendulums or springs and it asks anything about energy, try to use some form of conservation of energy. Look at where things are maximum in one direction or the other. So all of your energy here is potential. All of your energy here is kinetic. It makes solving those problems a lot easier. All right, pendulums. Moving away from springs, let's take a look at something that just swings back and forth. This is known as a simple pendulum, where all of our mass is at the end and we don't have to worry about the mass of the string at all. It's considered a light string, or it might even specifically say negligible mass, or we can ignore the mass of the string. All of our mass is at the end. Okay, so if I kind of freeze that in motion, here's our mass. There is a tension force pulling back up, and we can break that tension into different components using similar triangles. We can take a look at the displacement angle. How far away are we from vertical? So if this is vertical, then that's how far we are away from vertical. We can find our components of the force, where the force here is really the weight. So our cosine here is going to give us the component that balances out tension. And then sine is going to give us the component that this is the force trying to restore back towards the center of the path. Now, I'm going to talk about this real quick. When this pendulum mass, it's often called a bob, swings all the way to the bottom, this is the lowest position that it's going to have. And over here to the side, or if it's on the other side, that's the highest position it's going to have. So if we're talking about things in terms of conservation of energy, that's the height that we're looking at for gravitational potential. And how we get that height has to do with the length of this cord. And then we want this component. And if you're in degree mode, then we're going to look at the sine of theta. And I'll show you a trick if you're in radians where you can just use theta itself. So on your formula sheet, back with the other period of a spring, now we also have period of a pendulum. This is going to have a little P down here to remind you this is for a pendulum. The time for this to go from the right to the center, to the left, to the center, to the right, that's one period, is 2 pi root L over G, where L is the length of the string. Notice that the mass hanging on the end is not in this equation at all. The mass hanging on the end does not affect a simple pendulum. So it doesn't matter if you have a small mass or a large mass. That does not affect how fast it swings back and forth. All right, so with these simple pendulums, what College Board usually talks about are small displacements, so an angle less than 15 degrees. If we're talking about a small displacement, then a pendulum does act like a simple harmonic oscillator. Excuse me. So if we assume that that string doesn't stretch at all, we can ignore the mass of the string, and our restoring force is what we were looking at previously, is the weight and then the sine of the angle to give that component that restores it back to equilibrium from either side. Whereas the tension is the weight and cosine of the angle. So different components of the forces. So that displacement, the height, is the length of the cord times theta, and you can just call it theta. There we go. All right, you can call this theta. as long as your calculator is in radians. So there is a little property called the small angle approximation that you can use in radian mode. So if you've got your calculators handy, put it in radian mode. And then we want small angles. So if we're talking less than 15 degrees, that's less than about 0.3 radians. So take a look at the sine of maybe 0.1, the sine of 0.2, the sine of 0.3, and you should notice that the sine of that angle is almost identical to the angle itself. So that's just a way to kind of speed up some of your calculations to find that component. Now, if you're still in degree mode and you just want to leave your calculator in degrees for the whole thing, so be it. And then you just have to take the sine of that angle. So again, the period of a pendulum is 2 pi root length of the pendulum over g. Now, something to point out just with this equation, on the free response portion of the AP1 exam, there's probably going to be a question based on labs. That's not what we're looking at tonight, but this equation is a really easy way to measure what is G where you are. You can create a pendulum and you can measure L really easily, and you can measure the time back and forth pretty easily. I wouldn't do it for one period, but maybe 10 or 20 going back and forth and then divide by 10 or 20 to kind of even out some of that error, and plug into this equation or graph this and you rearrange it algebraically, and you can get what is G for your spot on Earth, or if you're on the moon or on Mars or wherever. So keep that in mind if you end up having any kind of a lab-based question that talks about how would we find the experimental value of G. All right, well, we are going to kind of switch modes at this point, and we're going to go to a pair deck. Hi, everybody. So let me find my pair deck, please. Where did it go? Oh, we're launching. All right, so if you go to joinpd.com, now that that's finally launched, our join code tonight is FJIXWC. The space doesn't really matter. Capital doesn't really matter. So go ahead and log into that. And we're going to take a look at some multiple choice questions together. Fragrant Jacks instantly X-ray warm carrots. All right. All right, we're almost to half of our participants logged into Pear Deck. Getting there. And while we're waiting for a couple more seconds here for others to join us, those of you that are logged in, make sure that you've got a calculator handy, that you've got your equation sheet handy, and maybe something that you can scribble some calculations on to figure out what's going on. All right, we're going to go ahead and start. The join code is still up here in the corner. So for those of you who haven't joined yet, you can join in. These are the review questions themselves. So let's see what we got here. All right, if we have a mass of 0.5 kilograms connected to a massless spring, so we've got this magical spring here, and this force or spring constant here is 80. The system oscillates on a frictionless horizontal surface. The amplitude of the oscillations is 6 centimeters. Let's see if we can figure out the total mechanical energy of this system. Oh, no, Matt, do you have any idea why the little dot's not showing up for everyone to drag around?
I do not.
Very sad.
Let's see.
All right, well, we're getting some
Yeah,
responses.
I don't know.
Okay.
Okay, so she said, so the participants are saying they're seeing a dot.
Good. So drag the dot to what you want to choose. Is it A? Is it B? Is it C? Is it D? You got a red dot there. Drag it to where you think the answer needs to be.
You should be able to show responses and then you'll be able to see where they're at.
Right. All right. Well, there we go. 30 people out of 44. Ooh. Oh, we still got some stuff moving around. A, B, C, D. All right, so to solve this, we have our mass, we have our spring constant, we have our amplitude. We don't really need the mass for this, because what we're going to take a look at for the mechanical energy, at our maximum displacement, all of our energy is spring potential energy. So we can use that spring potential energy equation, 1/2 kx squared. Just make sure your units are in the right format. Then we should get 0.14. That was answer choice B. Our next question. We have a mass, 0.8 kilograms, attached to a vertical spring. It's observed that the spring stretches 0.150 meters. Let's see if we can find the spring constant on this spring. Lock in your answers. Okay, still a few more responses that we're waiting on. So take that orange triangle, put it where you think it needs to go. All right, let's see how we're doing. We're still spread out. A whole bunch of people said A, B, and C. A few people said D. All right, so what we're looking at. Whoops, that's the wrong way. There we go. We're going to use Hooke's law here. We're given that spring constant. Or we're trying to find the spring constant using Hooke's law. We're given the force. We're given the displacement. So we can find our spring constant, F divided by X. And we're not going to really worry about that negative because, again, on your AP equation sheet, it's just absolute value. All right, now our next one. Mass of 0.6 kilograms connected to a massless spring. We have a force constant, this time that's given to us, of 80 newtons per meter. And this system is oscillating on a frictionless horizontal surface, so it's going back and forth. The amplitude of the oscillations is 9 centimeters. What is the speed when we are 3 centimeters from the equilibrium point? This one's going to take a little bit more calculating, just as a heads up. So if you got some scratch paper there, let's draw it out, figure out what's happening, and when you're ready, you can drag that little hexagon to either A, B, C, or D. Yeah, this one's going a little slower. So some key things to think about here. The maximum amplitude is at 9 centimeters. So you can calculate what the total amount of energy is as spring potential at 9 centimeters. And then take a look at what is the energy at 3 centimeters and in spring potential. And the rest of it's going to have to be in kinetic energy because we have conservation of energy here. So try that. We're halfway there. Come on, guys. You can do this. All right, going once, going twice. Let's see how we're doing. So the bulk of our responses seem to be around B and C, somewhere in there. Those are wildly different speeds. So let's see. All right, so at our maximum displacement, we plug in all what we know, we can find that the total amount of mechanical energy is going to be spring potential for 0.32 joules. We still have the spring pulling on this mass at 3 centimeters. So we still have some spring potential energy at 0.036 joules. And the difference is going to be our kinetic energy. So B is going to be our correct answer there. All right. Here we have an object attached to a horizontal spring. It's set into oscillation motion. The position sensor here is used to record the displacement of the object from equilibrium as a function of time. So we have our displacement over time. And this is what we get. The total distance traveled from time 5 to time 9 would be what? Not a whole lot to actually calculate here. This is, can you read and interpret a graph? So as you go through the multiple choice questions on the AP exam, you're going to have under 2 minutes per question to answer in order to get through all of the questions in the time that's allowed. So you need to look at graphs and things like this, just like this one. Is there something that we can quickly analyze to maybe get some extra time on a different question and take less than the maximum time on this one? Yeah, so that was a key in the chat. It's asking for total distance, not total displacement from time 5 to time 9. Ooh, we're all over the place again. All right, so let's talk about this. The object is at a position of negative 20 centimeters at time 5. And it made it all the way to 0. So that's a distance of 20. And then it gets to a distance of positive 20 on the other side. So that's a total of 40. And then it's going to creep back. That gives us C as our correct answer. It travels 80 centimeters in distance. So make sure that you're answering the question that's being asked, not just assuming. Assuming is bad. Most of us know that. So this is asking distance, not displacement. All right, another one with the same graph. The object attached to this horizontal spring, it's set into motion. We have our position sensor again. It's recording displacement as a function of time. And here's our graph. What is the frequency of the oscillation? So frequency is the how many of these cycles in 1 second? And if you're using your equation sheet, there's a little cheat that you can use to make this easier. I'll show it to you in a little bit. But look at how frequency and period of time are related to each other. So again, look at what you can see on the graph. What is easy to measure on the graph? And how is that related to other things that we can determine about this oscillation? Oh, we're getting there. About 10 more people need to put in an answer. Come on, you can do it. You can do it. You can do it. Let's see our distribution. Well, I'm glad to see that most of us are staying away from A. That's awesome. All right, so looking at our graph, probably one of the easier things to do is to figure out the time it takes for one complete oscillation, which was kind of hinted at the previous question. So like from time 5 to time 9, that is one complete oscillation. That is 4 seconds, and that is the period. And if you look on your equation sheet, it shows you that period is the inverse of frequency, or frequency is the inverse of period. So 1/4 seconds, or 1/0 gives you 0.25 hertz. So that is answer choice B as in boy. Good job. All right, next one. We have a mass oscillating on the end of an ideal spring. Again, an ideal spring just means that you can stretch it and compress it. We're given the spring constant of 90 newtons per meter. The maximum velocity of this mass is 12.8 meters per second. So find the total mechanical energy of the system. You have plenty of information here to calculate the total energy of this spring mass system. So think about how you would do that. Let's see how we're doing. Oh, a little bit more than half. All right, so let's think about what's happening here. Where is the point in the path where you're going to have the maximum velocity? You're going to have the maximum velocity at equilibrium. And if we're at equilibrium and we have a velocity, we know we have kinetic energy, but at equilibrium, x is 0, so we don't have any spring potential energy. So all of our energy is kinetic at equilibrium, and that's our maximum speed. So let's see if we can plug all that into our equation and get an answer. Oh, answers are coming in a little bit faster now. All right, so again, we're looking here, the total mechanical energy where we have the highest velocity is going to be as we go through equilibrium, and all of the energy is kinetic. So 1/2 times the mass that we're given times our velocity squared gives us 65.5 joules, which is answer choice C. Good job. All right, same spring, bouncing back and forth. This time, however, we want to know the maximum displacement of our mass. So we still have that 0.8 kilograms. It's oscillating horizontally. Our spring constant is still 90 newtons per meter, and our maximum velocity is still 12.8 meters per second. But how far to the left or the right is this going to either stretch or compress? So drag that purple heart where you think it needs to go. All right, we seem to be kind of split between two of our answer choices. Keep going. We can use some of the information from question 6 to figure out question 7. It's the same spring, so we have the same total mechanical energy. But think about where you're going to have the maximum stretch. What kind of energy are you going to have when you're at maximum stretch? All right, maximum stretch is where the object stops moving and turns around. So all of our energy ends up being spring potential energy, 1/2 kx squared. It's the same 65.5 joules that we had in question 6. It's the same spring constant. So we're just going to rearrange this algebraically, and we end up with 1.21 meters. And like I said, we were pretty much split between either that or the 1.4. So you were pretty close if you chose B, but the answer is D. All right, our next one. We have an object on a spring and it's creating this wave-like pattern. Okay. So we have a 0.4 kilogram block with a hole in the middle of it on a spring, and there's a rope attached to it, and that rope is also attached to the wall. So we're bouncing this rope up and down, and we get the same kind of graph pattern that we got using a motion detector earlier. Okay, so when the block is oscillating at 20 hertz, we get this wave pattern, a standing wave that's shown here. Let's see if we can figure out the spring constant based on that diagram. So look at your formulas on your formula sheet. Which formulas on that sheet involve the spring constant? And how is any of that other stuff related to this wave that we see here and the information that we're given? All right, so we have this wave. We know what the frequency is, and we talked about this earlier, that frequency, if you flip it upside down, 1 over the frequency is the period, which would be the time from, say, crest to crest or trough to trough, or where it's crossing our equilibrium. Okay, so it's that repeated time. So period is going to be 1 over 20. And period on our formula sheet is for a spring is equal to 2 pi times the square root of the mass over the spring constant. So we can rearrange that and see if that changes anybody's response. We've got at least one response for every single answer choice. And I guess my other word of advice for you guys, because I'm watching some of your responses in real time here. Go with your first instinct. Unless you have some specific reason to change your answer on the AP exam, your gut instinct is usually correct. Go with that and stay with it. What do we got? A little bit more than half of us have responded. Come on. All right, let's see what we get here. As I said, frequency, flip that over and we're going to get the period. So 1 over 20 hertz gives us a period of 0.05 seconds, and we can rearrange our formula to get K by itself. So we end up with a pretty high spring constant here, a little over 6,000. So it's already a little bit after 8. For those of you that can hang out with me a little bit longer, I'd like to go ahead and just kind of jump over to a free response question. Let's try that out. So we're going to skip ahead. Oops, there we go. To a free response. If you got to go, I get it. But here we go. This is one of our longer questions, but we're going to only look at part of it. It is a 12-point question. They estimate 25 minutes. We're not going to spend 25 minutes on it, but let's start off with this spring on a track. So we have a block initially at position 0 on a spring that's just sitting there minding its own business. The block is then pushed along that frictionless surface to position -D. So that compresses the spring. And then it's released and it pushes forward. And here's where it gets interesting. It's going to hit a rough part of a track, which means we've gone from 0 friction to what do we do when there is friction? Excuse me. So we're going to try drawing on a graph what happens between -D and 3D. So we're starting at 0, we can push it to the left, and then it moves over to the right. So think about what you would put for kinetic energy and what you would put for potential energy on our graph. And you should be able to just draw on the graph. So again, we are starting at 0. We push it to the left to a position of -D and then let it go. What's it going to do as it goes from -D to +3D, both for kinetic and potential energy? So again, it's on a smooth, basically no friction for the first part, and then it starts to hit some friction as it goes towards 3D. We've got some good responses out there. How are we doing on drawing? Oh, we're almost halfway. Come on. You hung with me this far. Let's see what you can come up with. All right, so I'm going to back this up just a second so we can go back to our original scenario. So we're moving from -d to 0, and then we're continuing out to 3D. Let's talk about what's going to happen to the, I don't know, how about the kinetic energy? We're going to start off with 0 kinetic energy. And it's going to increase as it gets faster and faster and moves towards 0. And then once we pass 0, that kinetic energy is going to decrease because of friction until it finally comes to a stop out at 3D. Meanwhile, for potential energy, the spring is at a maximum amount of stretch at -d. So we have lots of spring energy there. And that's going to go to 0 when we get to the center. And then after that, the spring's not involved at all. So we don't get any more spring energy. So let's see. So here we've got the kinetic energy. It's going to increase from -d to 0, and then it's going to decrease until we get out to 3D, whereas the potential energy of that spring decreases until we get back to equilibrium, and then the spring's not involved at all. Notice where the points come from. So it talks about a point here for sketching a curve that is reasonably correct. It doesn't say it has to be exactly correct. It says it has to be reasonably correct. Okay, so that from between x of -d and 0, we've got maximum and minimums shown. So some of you gave me straight lines there instead of a curve, even though these kinetic energy and potential energy are both have something squared in them. That's fine. They would take that. That's a point. For sketching that the two curves from negative d to 0, such that the total energy is constant. So they're going to cross over, and the amount of U and the amount of K always adds up to about the same value. Most of you gave me that. For sketching that the potential energy is 0 after X equals 0. Okay. So for that part where it's sliding past the spring's not involved anymore. There is no more potential energy. And that the kinetic energy is a linear function because of friction forces slowing this down. Yeah. The object is not going to get pulled back by the spring. It's resting against it, so the spring pushes it out, but it's not actually attached. So think of this kind of like a pinball machine where you pull that lever back, and once that spring releases, it's going to push the ball in front of it, and the ball just takes off. So that's why it doesn't oscillate back and forth. It's a good question. All right, we kind of skipped the other parts of this question, but let me go back to it. In part B, we have some new information here, so the situation changes slightly. We know this because there's information all the way to the left justified, not indented. So the spring is now compressed twice as much. We go to 2D. The student is asked to predict whether the final position is going to be twice as far. Is it going to move to the right all the way to 6D? The student reasons that since the spring will be compressed twice as much, the block will have more energy when it leaves the spring, so it will slide farther along the track and stop at position 6D. Is anything correct? And is anything not correct? For this, basically, give me your thoughts in the chat. What do you think is happening here? And as pointed out in the chat, questions like this where it says, is anything correct or not correct? And what is correct, what's not correct? Those are really common on the exam. Anybody got some thoughts? Are we just getting tired tonight? So if we look at the formula for spring or elastic potential energy, 1/2 kx squared. If I double x, am I doubling the amount of energy? Do we increase the energy when we stretch it further? What do you think? Yes, definitely. So as far as what the student got right, yes, we're going to have more energy by stretching it more. But did we double the energy? What do you think? You got a 50-50 shot there. Yes, Mary, we would actually be quadrupling. So are we going to end up at 6D at the end? Probably not. We're going to end up somewhere else. It's not a linear relationship. We do have that x squared. So when we increase x, we increase that by squaring it. So the student is correct that it's going to have more energy, but it's probably not going to end up at 6D. And as far as scoring that, that was 1 point for each of those. You don't have to go into super minute detail on any of this, what is correct and what is not. All right, see? Quantitative reasoning. We can use equations. Can we figure out where that new position is going to be? We kind of danced around that a little bit. So let's look at the key here. We can look at our starting potential energy and then our new potential energy. So yes, we are quadrupling the amount of energy compared to what we started. And work. Hey, remember energy and work are related with the work energy theorem? We can look at that force times displacement, and the force that we're looking at here is friction. So mu times the weight times our displacement. We can calculate through this. So we actually end up going to 12D, which proportionally we should be able to figure out. If we have 4 times the amount of energy, we're probably going to end up 4 times farther. So instead of 3, it's 4. 12 here. And then the last part, here we go. This is the question itself. Explain how any correct aspects of the student's reasoning identified in part B are expressed in that mathematical relationship, and how any incorrect aspects are identified in your relationship. So College Board wants you to go back to this set of, showing your work. How did you go from point A to point B? What steps did you take? So what was correct? We said that, yes, there's going to be more energy if we stretch it back further. And we see that here, that potential energy 2 is 4 times what potential energy 1 was. So that is supported. And then our final answer, we said it's not 6D. It ends up being 4 times 3 or 12D. So the student was wrong that it's not going to be 6 times far, or twice as far at 6D. It's 4 times farther. So both of those support what we said back in part B. College Board is not trying to trick you. It's trying to lead you through and use what you've just answered in the next part. So a point for indicating that, yes, we have more energy. A point that we are going to go farther, and a point to say here's our incorrect, that it's not a linear relationship. All right, so that's really about all we have for tonight. I hope that going over some of these things maybe freshened up some of those memories from when you talked about it in your own classes, or clarified some things along the way. If you have questions, by all means, send them in. We'll see what we can do to answer. But thank you so much for being in here tonight. We'll have some more of these sessions, so stay tuned. Emails will go out to your teachers as soon as we can get those set up. And we hope to see you back at some of those. Have a great evening. You are all welcome.
Nice crowd tonight.
Yeah,
I think in and out, we had over 70.
that's pretty awesome.
Yeah. Really good. And they seem to be from kind of all over the place too. I think there was a lot of Kim students and several of yours, but
Right, and mine were back from the fall because we're on a semester by semester schedule. So
Right.
I don't have any AP Physics 1 right now. They were
Gotcha.
they all finished in December.
Gotcha. Well, this was good timing for them then.
Yes.
All right. I've got a date for the next one of these on the calendar. I'll have to look it up, but I'll send it to you. And if you want to do it, you are more than welcome to do it. But I'll email you the date here in the next day or two.
Okay.
I think it went pretty well.
So do you know what the next topic is going to be?
I don't off the top of my head. I'll look it up and send it to you. I've got it worked out, but I don't know off the top of my head. I've got
Okay.
a mock reading tomorrow, so that's where my brain has been today is on the mock reading.
Fair enough.
But I'll get it to you tomorrow.
Okay, no problem.
All right, we'll see you soon. Thanks again for doing this.
Yeah, no problem.
And you know how to put you know how to do the Chrome River thing?
If you could just send me what the rate is for this,
Yes.
I think I can do the rest.
I'll see. I shall have got some step-by-step direction, so I'll send you the step-by-step.
Okay, appreciate it.
All right, see ya.
All right, bye.
Bye.